Okay, right, morning guys. We have around 55 minutes to 1 hour session. So just like attention on the syllabus, as you know, syllabus is very important. Whatever it states in the syllabus, these are all for the organic stuff. I can upload this to the classroom material later on, but you should know that this document is available for free about 2 years before 2022. They already told the teachers and the students who are going to sit for the exam, the curriculum, that what is to be expected in the years to come. These are all the functional groups. Okay, they are not in the right orientation, but when you print them out, they'll be all right. Identifying amine, nitriles, ester, carboxylic acid, alkane, alkene, halogenoalkane, alcohols, the carbonyls, ketones. Sorry, this is ketone. This is aldehyde. So it's RCHO, alkyl and alkyl, carbon and carbon next to the carbonyl, carbon and hydrogen next to the carbonyl is aldehyde. This is ketone. These are all just AS level chemistry. Of course, you need to know how to name. You need to know skeletal formula, display formula, as well as structural formula. I didn't mention it there, but it is in the syllabus as well. So I thought that organic chemistry is not, it's quite a big chunk of materials for me to actually cover it through one-by-one review. And that is actually supposed to be your AS learning materials. You're supposed to have covered them one by one based on the learning objective. So what I thought would be quite nice is these are a set of questions, and organic chemistry question is not standalone. It's not like topic by topic. It's rather different concepts combined into one, such as these sample questions. These are combination of questions over the last couple of years. Doesn't matter which year you take it from. As long as it's organic, you should be able to do it because they are from the syllabus. So yeah, I've just combined quite a few questions from different topics. Each of these paper is around 2 hours. Obviously, it's much longer than your AS level paper, but because it's all organic, and I thought the time is appropriate, the duration is appropriate, given the complexity of the concepts as well as the grand total of the marks available. So the first section consists of this thing called Introductory Organic Chemistry. So the intro organic include the type of reactions, as well as isomerism, as well as naming and drawing all those skeletal, display, structural, and stuff. The second bit will be your alkane and alkene. So the alkane will come under like distillations of the crude oil, the fractional distillation of crude oil, the different fractions. The alkene will have the bigger chunk of the chemistry, such as the mechanism and oxidation reactions of alkene, etc., etc. You also have, I think, alcohols chemistry in here, and you got together with alkene part of polymerization. So in the other paper, in the other big chunk of the paper, there will be the carbonyl, the mass spec, the infrared, the carboxylic acid and esters in the other paper. So let's just go through this one first. Do you want me to go through question by question, or do you want to just raise up your question first? Any thoughts from you guys? Hello, hello. Can you hear me? Any thoughts on what you... Sorry, what did you say, Shakira?
Up to you.
Up to me? Okay. Okay. I thought it'd be quite nice if I let you guys ask some questions first. All right. I'll open the floor for you guys to ask me to go through any question first. So the paper was already provided a week in advance. Yeah. So, it's really, like I said, up to you to tell me which question you want me to go through. So you can just tell me the page number or just direct me which question you want me to go through. Come on, chop chop. Anything from you guys? Nothing? People are quiet this morning? But people want me to go through organic, right? But like, are there specific things that you want me to go through? It's such a big concept. Well, I guess while waiting for you to figure out some questions, I should probably go through this first one. So these are basic definitions. So definitions will always be worth 1 to 2 marks. So we know about structural isomers from your O-level studies, because the only isomerism you learn in O-level is what you call structural isomers. So structural isomers, they are molecules, they are compounds with the same molecular formula, So from your definitions in topic 1 on calculations and more concept, molecular formula are the actual number of atoms in one single molecule. But then what is different will be the different structural formula. So you should also know that structural isomers are divided into 3 specific branches. So let me just quickly show you some stuff. So structural isomerism can be divided into 3 main types. The first one is what you call position isomer. So from the name itself, you would have heard of things like 1-chloropropane. So I started drawing some skeletal formula. In the skeletal formula, make sure that you know that carbon form 4 bonds. That is the most important concept. So if carbon form 4 bonds, the carbon here, you don't show the hydrogen bonded to the carbon. The carbon here form 1 bond to the carbon. So that means there are 3 hydrogen, which you don't see. So this is a CH3 at carbon number 3 there. Now the next one, carbon number 2, carbon form 4 bond. That is something you have to keep telling yourself in your mind. Carbon form 4 bond, you see 1 and 2. So there must be CH2 there. So there's CH2. Carbon form 4 bond, 1 and 2. So there must be 2 hydrogen, which you don't see there, like that. Of course, you can draw the display, but I dare you to draw display in your A2 paper 4 organic, or in a multiple choice question, and you will find that you just don't have enough time. Okay, so skeletal is the best and the most elegant way to go about doing organic chemistry. Now this one here, the longest chain carbon is 3 carbon. You will see that this is called 2-chloropropane. So 3 carbon is prop. This is halogenoalkane, is propane. The chloro, bromo, iodo, they are prefix, so we put them in front in terms of the position of where the halogen group is. This is a CH3, CH bracket Cl, carbon form 4 bonds. So 1, 2, 3, there is 1 hydrogen remaining. The Cl is the branch, and then CH3 there. If you total out the number of carbons, this is C3H3 4, 5, 6, 7. So this is also C3H7Cl. You will see that this is called molecular formula, the actual number of atoms in one single molecule, the actual number of atoms in one single molecule. This is what you call structural isomer, structural formula, because you can see the structure from the formula itself. If you cannot see the structure itself, it's not called structural formula, okay? Now this thing is called skeletal formula. I'm not gonna draw display formula because that is taking quite a lot of time there. Now, the other second bit of structural isomers will be something called chain isomer. So chain isomer is straight chain versus branch chain. So this is a straight chain, this is a branch chain. So straight chain versus branch chain, they are chain isomer. So here you will see that there is 1, 2, 3, and 4. This is what you call butane. The longest carbon chain is only 3 carbon, which means this is a branch, and this is a 1 carbon branch. So it's a propane. So I'll name the longest chain carbon first, alkane, and then it has a branch. The branch is 1 carbon. It is a CH3, is at position 2, so it's 2-methyl propane. So these 2 are what you call chain isomer. The very last one is something that a lot of you don't actually realize, is what you call functional group isomer. There is a reason why aldehydes and ketones are in the same topic. So aldehyde and ketones are what you call functional group isomer. I can show you one example if you don't believe me. So this is a 3-carbon aldehyde, CH3, CH2, CHO, 1, 2, and 3. A 3-carbon aldehyde. Can someone name me a 3-carbon aldehyde? Let me ask, I don't know. Rahiman, what is the name of 3-carbon aldehyde? How do you name 3-carbon aldehyde, Rahiman? Sorry, say that again. You are breaking up. Can you say that again, please? Do you know how to name aldehyde? You have problem naming aldehyde?
Yes.
Okay. Aldehyde has the Al at the end. It's not OL. OL is alcohol. It's got Al. So you started with just now 1, 2, and 3 carbon. So this is called prop, but it's propanel. So it's like methanel, ethanel, propanel. So it's got the AL at the end. So be very careful, yeah? Okay. Now ketone, the carbonyl next to them is carbon and carbon. So it's not hydrogen. This is hydrogen. We don't show the hydrogen bonded to the carbon in skeletal formula. So just from the one question alone, I can tell that people are not even okay with the first bit called introductory organic chemistry. You cannot expect to build a house with very weak foundations, yeah? Like you said, people find organic chemistry difficult because they didn't start from the very proper beginning. Start from naming, start from drawing, start from knowing the functional group and how to name them, okay? You gotta take one step back and think about what makes you struggle in the first place. So this is a ketone. The ketone there will have ONE at the end. It's a 3-carbon ketone. It's called propanone. Anyway, if you total up the number of carbon there, there's going to be C3H6O. And on the right side, you have C3H6O. Molecules with the same molecular formula, but different structural formula. They are called structural isomers. But not only their structural isomers, structural formula are different, they also have a different functional group. That's why functional group isomer come under structural isomer. Aldehyde and ketones are not the only functional group isomer. There is another one. It's also in your AS topic. It's called carboxylic acid and ester. So not too sure if you have been taught in this manner, but these are common things which I usually teach students when I was teaching A-levels. But there's a reason why these two are in the same topic. There's the reason why these two are in the same topic, okay? You can see how the questions are going to be asked usually. So for instance, if I have a 2-carbon carboxylic acid, this is a carboxylic acid, which I don't want to ask because I don't want to be disappointed, but I'm sure you know what is the name of 2-carbon carboxylic acid. It's called ethanoic acid, okay? Now I'm going to draw an ester. So you might not be very happy with me drawing skeletal formula, but you cannot do anything because, you know, in Cambridge exam, they give you skeletal formula. Number one, either you know how to read it, or number two, you just can't answer the question. That's it. If you don't prepare yourself to do skeletal formula, you're like, you wait until tomorrow. Well, there's not going to be tomorrow since the exam is going to be happening. So, you know, you need to know what is happening. The C double bond O, that is what you call ester, okay? Then there is one hydrogen here because you don't show the hydrogen bonded to the carbon. So it's H, and then CO2, and then a CH3 at the end there. When I form ester, I always think about this ester linkage. Well, this whole thing is ester linkage, but this bond here, the CO single bond, that is the new bond that I've formed. So what I can see is this bit is the carboxylic acid bit because you get ester by combining a carboxylic acid as well as an alcohol. When you name ester, you name the alcohol first. When you name ester, you name the alcohol first. So you're going to get methyl from the methanol, and then you get the methanoate from the methanoic acid. 1-carbon carboxylic acid is called methanoic acid. Why not 2 carbon? Because 1 carbon there plus 1 carbon is 2 carbon. 1 carbon plus 1 carbon is 2 carbon. You know why I stick with 2 carbon? Because we have to think about C2H4O2, C2H4O2. Molecules with the same molecular formula, different structural formula. They are what we call structural isomers, but they have different functional group because functional group isomer come under the umbrella of structural isomerism there. So 3 different structural isomers there. Don't get confused, yeah? These are introductory organic chemistry there. Anyway, chiral. Can someone tell me what is meant by chiral? Shakira, are you there? There are 2 Shakira. Shakira Kolani. Can you tell me anything about chiral? Hello, hello. Shakira Kolani, are you there?
Sir.
What can you tell me about chiral?
Something to do with the structure has a, I don't remember what's the name, hexagon shape, is it?
I wish you could use that reason in the exam. You're like, I don't know what I'm supposed to know. Okay, so a chiral carbon or a chiral center basically is a carbon atom bonded to 4 different groups of atoms, okay? So this is under stereoisomerism actually, bonded to 4 different atoms or groups of atoms. It doesn't have to be atoms, it can be groups of atoms, meaning it can be alkyl or something else. But what is very important is carbon form 4 bonds. So all the 4 groups or all the 4 atoms that is bonded to has got to be different in order for you to have chiral center. Of course, then after structural isomerism, the other thing you learn in AS, Introductory Organic Chemistry, is something you call stereoisomerism. So stereoisomerism has its own meaning. So they have the same molecular formula, but they also have the same structural formula. So that's why you don't call them structural isomers. You call them stereoisomers because there is something which is different about them. And stereo there means in 3 dimensions, in space. So how they are arranged in space, okay? They have different arrangement of atoms in space, different arrangement of atoms or groups in space. And this comes down to 2 different stereoisomerisms, one of which is called optical isomerism. And then the other one is called the cis-trans, or you could call that the geometric isomerism. The cis-trans is not actually the official name. It's supposed to be geometric, but people do accept it as cis and trans. Now, the main requirement for cis and trans, a lot of you would know this. What is the requirement for cis and trans? Isa, are you there, Isa?
Yes.
Yeah, what are the requirements? When do you have cis and trans?
Different functional group.
Nope. Akila, do you want to correct her? Do you want to correct Isa? What is the requirement for cis and trans isomerism?
Having 2 same functional group.
Oh no. Okay. Shakira, Nabila, do you want to correct both of them? What is the main requirement to have cis and trans isomerism?
Carbon-carbon double bond.
Okay, I'm glad someone got it. Okay, must have carbon-carbon double bond because then you will prevent or you will restrict the rotation. Because if you remember about your pi bonds, this is a double bond, so you cannot really. So it's a trigonal planar center, right? If you think about your hybridization, it is a sp2 carbon. But then there is 1 p orbital, which is unhybridized. And when they form the pi bond, they prevent you from rotating freely about this single bond because you have a double bond. But the number 1 mistake is people thought that, oh, double bond must have cis and trans. Not necessarily. And that is where I think some of you, just now Isa and Akila must have been confused about. The other condition is and must not have. Now this one is must not have. Just now was must have. Now is must not have. Must not have 2 atoms or groups of atoms that are the same. So you cannot have 2 groups that are the same on the same site, on the same carbon of the carbon-carbon double bond. So what do I mean by that? So first of all, carbon-carbon double bond, yes, you must have it. Now you must not have 2 atoms or groups. They are on the same carbon of the carbon-carbon double bond. So I'm just going to show you an example. So when you have this thing here, first of all, you have carbon-carbon double bond. Now, you have a hydrogen and a CH3. Hydrogen and CH3 are different. So they are not the same. Therefore, they are okay. Now you're looking at this carbon here. You have CH3 and you have hydrogen. They are not the same. So you can have cis and trans for this molecule here, because what I've drawn there, you can see that the different groups here, they are on opposite side. I've drawn it like that, but if you want, you can draw it like that also. It's just about the angle where you can rotate this slightly, and then you can get this better looking skeletal formula. But you can see they're on opposite side. They're on opposite side. These 2 are the same. Is this cis or is this trans, Akila? Akila, is this cis or is this trans?
Trans.
This is the trans isomer. And you should be able to draw the cis where I draw them on the same side. So this is now cis where they are on the same side. So there is geometric isomerism, there is cis and trans, okay? Now I'm gonna show you something else. Can you have cis and trans here? Can you have cis and trans here, Rahimat?
No.
Why not? You see, question will ask you, state and explain whether this thing will have geometric isomerism or not. So you said no, why not?
Two functional group is the same.
Your explanation is not as complete as I thought it would be, okay? So you don't really call them like functional group. You can say that the two groups, they are two CH3 on the same carbon of the carbon-carbon double bond, okay? So you want to try and explain the idea so that other people can understand them exactly as you want them to see it, because you are not writing a marking scheme, okay? I'm reminding all of you, okay? You do not have a marking scheme next to you. Neither do you know that the question will be a repeated question, because structured, I can ask you anything. That's the difficulty about chemistry, right? But the concept is the same. Elaborate your idea. Show the examiner what you're talking about. Get straight to the point, okay? So there is no cis and trans because you have the two groups, the two CH3, they are the same on the same carbon of the carbon-carbon double bond. Doesn't satisfy this condition, no cis and trans. But there's also another hint, okay? I will show you something else, okay? Can you have cis and trans here, Yasmin? Can you have cis and trans here for number 3? What do you think, Yasmin?
No.
Why not?
Yes.
Yes, why yes?
They have different groups.
Okay.
On carbon.
Okay, and I'll tell you, there are no cis and trans here.
No.
You are wrong. Okay, now your eye only want to see what you want to see because it's skeletal, right? And you cannot really choose when the question gives you skeletal. Your eye only see what you want to see. What you don't see are the hydrogen. Do you see what is here? How many hydrogen is here, Yasmin? Hello, Yasmin. How many
1.
hydrogen is here? 1. Okay, carbon form how many bond? Can you tell me carbon form how many covalent bond?
2.
Okay, carbon can form 4 covalent bond. What you see here is carbon forming double bond to carbon, right? So how many more hydrogen are here? Are you following this? Carbon form 4 covalent bond. That is what you have in your mind. Carbon form 4 covalent bond. You only show the carbon bonded to carbon or carbon bonded to something else. You never ever show hydrogen bonded to carbon in a skeletal formula. So here you show carbon-carbon double bond. So that means there are 2 more covalent bond, right? So that means how many hydrogen is here bonded to this carbon here? Are you okay, Yasmin? Look, Yasmin, what you have is like that. So CH3, CH2, CH3. Carbon form 4 covalent bond. I already showed 2 there, 1 and 2. So how many hydrogen is left on the carbon here, Yasmin?
2.
2, because that is what you do when you read skeletal formula. I can tell that people are not very experienced in reading skeletal formula. So guess what? You have a CH2 double bond, CH3, CH2, CH3. This is the structural formula for this isomer. There are no cis and trans because of this CH2 there. Remember, it's not just groups that you're looking for. You're looking for 2 atoms or 2 groups that are the same. Okay, same groups or same atoms on the same carbon, the carbon double bond cannot have cis and trans, cannot have cis and trans. Okay, now I'm going to introduce to you the very last thing that cannot have cis and trans. Okay, this thing is extremely difficult. So sometimes you get it in multiple choice, sometimes you don't. Okay, but when you get it in multiple choice, you will know it. When I have this thing, this is called a cyclohexene. Can I have cis and trans here? What do you think, Rahiman? Can I have cis and trans? Cyclohexene, right? So for your information, this has come in multiple choice a couple of times, yeah? Cyclohexene, can it have cis and trans or not? What do you think, Rahman?
Yes.
The answer is no. Okay, so you see there are always exception, right? There are always exception to like you're like, oh, double bond, yes, okay. Different groups, hydrogen and a carbon, hydrogen and a carbon. Then surely it can have cis and trans. It cannot. What is the reason? Because of the ring. The ring prevents it from rotating. So the ring has this thing in the direction of cis, right? If you make it trans, you'll be going the opposite way, and the bond cannot stretch long enough. Stretching bond is bad. It's because of the ring. Okay, it's like you have a snack and then you pull the snack around to make it trans. It's not gonna it's not gonna like it at all. So that's why there are no cis and trans when you have cyclohexene. Be very careful, yeah, everyone. Okay, I don't think they'll ask you this very often in structured questions. Anyway, going back to chiral carbons. I don't think it has been a good start, yeah, guys. I don't think you're prepared for organic chemistry at all. You're expecting me to, you know, get you from not knowing any organic to knowing everything about organic is almost impossible. You got to make that effort to actually go through the stuff on your own, yeah? That is before reactants and conditions like it, okay? So to show the chiral center, to show the optical isomerism, you must show three-dimensional. This is what they always insist. You must have like an imaginary mirror image here. And then what I do is I show the tetrahedral. Examiner reports have mentioned in the past, you've got to know how to draw them in tetrahedral very well. Some people, they draw tetrahedral like this. This is wrong, yeah? You cannot draw them at 90 degrees. You have to show the 109.5 degree tetrahedral geometry, show three dimension, okay? So make sure you know how to do that. And then follow the mirror image, flat and flat. So mirror means it goes the other way. Mirror means it goes the other way. So this is pointing towards this side. So I must have the bolded pointing towards that side, and then like that. And then I must put in the four different groups. I cannot just draw like that, yeah? So things will be like hydrogen, I don't know, OH, and then CH3, and then CH2, CH3, like that. So there will be CH2, CH3. So it really depends on your positioning of the atoms, really. So there's CH3, and then there's OH, and then there's H. Okay, be very careful about writing down the atoms so that you are not getting the order wrong way around, yeah? Okay, so hopefully that makes sense, the mirror images there. You will learn in A2, amino acids. Amino acids are also chiral except for glycine, because you have an amino group. So sort of like CO2H, that is the carboxylic acid group. This is the amino group. This is the H group. This is the R group. Glycine is an amino acid where R is the same as H. So there are no chiral center, but otherwise, apart from glycines, you will always have optically active amino acid that have optical activity. Have you heard of this thing called optical activity? No one is answering. Oh, okay. They will rotate. They will rotate plane polarized light. So they are like, how do you know it's chiral? Yeah, because it has carbon bonded to 4 different groups. How do you show in the lab? How do you show in the lab? What would you see? You cannot see the molecule, you see, but you pass it through plane polarized light. They will rotate plane polarized light. Okay, there's also something else called racemic mixture. Racemic mixture is an A2 concept. It comes under organic synthesis, which you will deal more with it in A2. Anyway, we're still on the first 2 marks. Oh gosh, okay, never mind. Now, the next thing, 2 structural isomers, which contain a chiral center. Now, this is 4 marks. They say give the structures. They don't say display, they don't say skeletal, they don't say structural. If it were me, okay, I'm teaching you, if it were me, based on personal preference, I would sketch quickly. I would sketch quickly. I only have limited time. I don't want to draw display, because if I draw display and then I make a mistake, I rub everything out. My paper is messy. I've wasted time. And then I started to get panic in the exam, if I were you. But now you're thinking, if you were me, you'll be thinking about 7 carbon, and I want a chiral center. So C7H16, this is 1, 2, 3, 4, 5, 6, 7, you see? Elegant, fast, and easy. Straight chain, no chiral center. This is all CH3, CH2, no chiral center. That is not what you want. What you want really is You want a center, 1 carbon, 2 carbon, 3 carbon. So let's see. So 1 carbon, 2 carbon, 3 carbon. Let's count our carbon. Longest chain carbon, 1, 2, 3, 4, 5, 6. Longest chain carbon has 6 carbon plus 1 is 7. But I must consider my numbering the other way also, because I don't know which way around will give me the smallest number for the branch. The blue color give me the branch at position 3. The red color give me the branch at position 4. So in naming, do we want the smallest number or the largest number? Basically, do we want the blue color naming or do we want the red color naming? I don't know. Shakira, Kalani, what do you think? What is the correct name? Based on the blue numbering or based on the red numbering?
Blue.
Okay, so you have at least done naming, all right? So do you want the lowest number for the branch? So that is also chiral. Carbon form 4 bond, carbon form 4 bond. This is skeletal formula. 1, 2, 3. So there is 1 more hydrogen there. Hydrogen is different group from 1 carbon, different group from 2 carbon, different group from 3 carbon. So this is definitely chiral center there. Okay, so hopefully that makes sense to you. That is your chiral center there. Anyway, I'm just going to make my diagram a little bit neater. So skeletal formula is acceptable here because they don't mention specifically what they want. 6 carbon alkane, so that is hexane. But then I've got a branch. The branch is CH3. The CH3 is called methyl. The methyl is at position 3. So 3 methyl hexane there. That is my number 1. Now they want the structure and name, so make sure you answer both of them. How about the second one? I don't know. Can I get the second one? How in the world do I get the second one? 2 structural isomer which contain chiral center. I hope I can get the second one though. This is tricky. Oh yeah, I can see the second one. Okay, now follow this one. When you got 3 carbon like this, you can branch. You can branch the 3 carbon. You cannot branch a 2 carbon. You cannot branch a 1 carbon, but you can branch a 3 carbon. So keep the same skeleton. Keep the same skeleton as just now. So same skeleton. Now I'm gonna have 4 and 5, and now I'm gonna put it here. So 3 carbon can be straight chain, 3 carbon can be branched. So this skeleton is the exact same thing. This is 2 carbon, this is 3 carbon, this is 1 carbon. So this is still a chiral center. I'm gonna do the exact same numbering as well. 1, 2, 3, 4, 5. And then just like any numbering, I have to consider other option as well before I decide. It's called decision making. So which one is better, the black color or the red color numbering? What do you think, Yasmin? Hello, Yasmin. The black color or the red color? Which one is the correct naming?
Red.
Red. Why? So you have just said something without thinking about the reason. And that is the number 1 mistake you can make in any A-level subject. You don't say something because you are forced to.
Like this.
Sorry? Hello? Do you remember the rules? The rules of naming, find the longest chain carbon, right? And do you want the largest number or the smallest number for your naming?
Small.
Do you want the smallest? Smallest for what, you see? Smallest for the branches. Smallest for the branches. So look at your branch. Your branch is at 3 and 4 for the red. If you use red, it's 3 and 4. If you use black, it's 2 and 3. So which one is better? 2, 3 for the black or 3, 4 for the red color?
2, 3, black.
2, 3 for the black is better because they will give you the smallest number. So I named the longest chain carbon first. It's 5 carbon. So that's what they call pentane, 5 carbon. Well, this applies for everyone, obviously, okay? If you are listening, you should really pick up your naming skill, yeah? 5 carbon longest chain is pentane, okay? And then I've got 2 branches. This is a methyl. This is also a methyl. So since both of them are the same, I combine them together to call them dimethyl. I have them at position 2 and 3. That is the lowest number I can think of. So 2, 3, 2, 3 dimethyl pentane there. I draw skeletal. I've saved my time. Without having to explain to you, I would have done this in 1 or 2 minutes in an exam. You see, this is the way your brain is thinking in an exam. You sketch, you don't just think in your head. You cannot do organic chemistry by just thinking in your head. You need to sketch, be ready to sketch, and be ready to think about the more sensible things, like knowing 3 carbon straight chain can be branched, 4 carbon straight chain can be branched. So, and then think about your naming, think about your numbering and stuff. Okay, hopefully that makes sense to you. Anyway, write an equation for the complete combustion. So heptane is C7H16. So, you know, you add it with oxygen, you're going to get CO2 plus H2O. So 7 CO2 because 7 carbon there, 16 hydrogen, you're going to get 8 H2O. 7 times 2 is 14 oxygen. 8 times 1 is 8 oxygen. 14 oxygen plus 8 oxygen is 22 oxygen. You have molecule here. You need 11 O2 like that to get your balance equation. Any equation which are not balanced, you get 0 in A-level chemistry. Now the next one, you need a solid pollutant. So you must produce carbon as a solid. Now they say an equation. So that means it could be any sort of equation. There could be different kind of product. As long as you produce a carbon as a product and you can get some CO2 or some CO, and if the equation is balanced, you get the 1 mark there. In terms of the environmental consequence for these unburned hydrocarbons, I hope you know that they can cause photochemical smoke. This is very, very particular. It is not carbon dioxide because they are talking about unburned hydrocarbon. This is stated in the syllabus. It's not carbon monoxide. It's not oxide of nitrogen. It's not carbon dioxide. So it's not things like greenhouse gas or whatever. This is unburned hydrocarbon, just lingering around in the air. They are specifically causing this thing, smoke there. They can cause smoke, they can cause breathing problems, all those kind of harmful consequences. I'm glad the first question is over. Well, you tell me what other question you want me to go through. Any other question you want me to go through? You choose the question now.
Question 3.
Question 3, okay. Whew, okay, not fooling around here. Okay, going for a difficult one. Okay, this is not actually difficult. Okay, in hindsight, yeah, this is probably all the time I have for today. Actually, let's see. Okay, so I'm going to be teaching you on something called chemistry of alkenes. Okay, we're going to be stitching up. If you know how to break up molecules, you should know how to stitch up molecules. Let's have a look at the total mark. 4, 5, 6, 7, 8, 9, 10. 10 marks mean 10 minutes. If you spend more than 10 minutes in this question, you know you're as good as done. Of course, if you go in not knowing anything, you are probably going to not make it as well. Now, this one is hot concentrated acidified KMnO4. First of all, you know H plus and KMnO4, that is going to be oxidizing agent. Now, what do we have here? We have these structural isomers with this molecular formula, C4H8, CnH2n. That should remind you of something called alkene. Alkene has carbon-carbon double bond. Carbon-carbon double bond, oxidizing agent. Have you done that before? Oxidizing agent does oxidation. You react this with alkene, so we are doing oxidation of alkene. Oxidation of alkene. I'm so glad you chose that question, Rahiman, because a lot of students, they forgot that they only thought it's addition reaction under alkene. Well, most of the reactions is addition reaction, but then there is also something else, part B, part C, they are called oxidation of alkene. Oxidation of alkene. Describe the following reactions. These are not A2, these are AS syllabus. Under the AS syllabus, you can get diol. So when you have alkene such as that, so when I have cold, dilute, acidified KMnO4, so you must have the acid for the redox to work. What happened is you will get OH and OH. You will get OH and OH. Pay focus on the OH and OH. This is called diol. Diol. Okay, this is oxidation of alkene. State the type of reaction, oxidation of alkene. Now they will try and confuse you. They will try and confuse you. This one is going to be CCH and then HCH3 is going to be OH and H. What you see here now is you only have one OH and you have another H here. So what have you done there? You have added H2O. This is addition of steam. You cannot add water liquid. You have to add steam. That is why this usually happens around 300 degrees Celsius. You need concentrated phosphoric acid catalyst. Now, this reaction is called addition. The type of reaction is addition reaction. It is not oxidation. This is oxidation. Both the carbon of the double bond gain oxygen. Here, only this carbon gain oxygen, this one gain hydrogen. This is not a redox. You know why they like to ask these two together? Because they know a student will make a mistake. You know, between this and oxidation, the type of reaction, the difference, addition versus oxidation. That was called dilute acidified KMnO4. The question you asked me, Rahiman, that was basically this one. This is the extreme oxidation. This is the serious oxidation, yeah, very, very extreme. Why do I call it extreme? Hot, concentrated. Previously, cold, dilute, conditions. Conditions, this thing is gonna rupture. Rupture means it will break totally. The carbon-carbon double bond, it's no longer just becoming single bond and diol, it totally breaks, And then we need to identify the subsequent product to determine the position alkene linkages. So that means stitch back. So they don't call it back, but from the products, you need to get back the alkene. That was basically this question here, what you asked me here. These are the products by oxidizing this alkene. And what you get then is, you get this product. From this product, stitch them back up to give me the structure of the alkene. All right. Now, based on this chemistry, I'm just gonna outline a couple of important concepts. So this is about the extreme oxidation. Yeah? This is the oxidative cleavage, oxidation. So this is using hot, concentrated KMnO4 acidified. Now, what actually happened? Well, let me show you an example. So if this is H, and this is, I don't know, CH3, H, what would happen is, you look at one side of the carbon-carbon double bond. This side is what you call CH2 double bond. They will get oxidized to become CO2 and H2O. This is from the CH2 double bond. Okay. Now, how about the other one? The other side, let me use a different color. Let me use black color, it's probably better. This is a R CH double bond. R group could be CH2, CH3, could be any carbon and then a hydrogen. So it's an RCH double bond. So what you will get is, when you have RCH double bond, you will get the R group, and then you get the carbon, and then the hydrogen will not survive, but the alkene there becomes a carbonyl, and that other one becomes carboxylic acid. You might think that, okay, I just changed that to become CO like that, I get aldehyde. But then this is oxidizing agent. You're under extreme condition and you're heating it up. There's no way the aldehyde will survive in this oxidizing agent since you are not distilling it. Therefore, you need to actually oxidize it all the way to carboxylic acid. So the RCH double bond gives you carboxylic acid. The original carbon there of the carbon-carbon double bond is this thing here. The original carbon there is this carbon dioxide. When you get carbon dioxide, it means you have CH2 double bond originally. When you get carboxylic acid, you must have an RCH double bond. How about when I have CH3, 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 CH3? Well, you can think about it. I'm going to break it out. I'm going to do the left-hand side first. So what I get is, if I have hot acidified KMnO4, so hot concentrated acidified KMnO4, so the RCR, this is RCR, could be the same group, could be different group, but it's carbon bonded to two different carbon. Carbon of the double bond bonded to two different carbons, that will give me ketone. Ketone cannot be oxidized further. If you cannot oxidize it further, so that means they just stay as ketone. This is your final product. How about the other side? Well, the other side, I look at the other side, CH3, CH3, I also get ketone because the other side is also RCR. Any carbon group bonded to the carbon of the double bond. So this is a RCR double bond. And then this is also a ketone, and they just stop there. And how many different products do I get here? How many different products do I get here, Rahiman?
2.
One. Because you realize something, they are the same. They are the same. They are called propanone. So that means I break an alkene, but I get one product. Why do I get one product? Because my alkene is symmetrical. Symmetry is your primary school concept where I remember drawing, the left side, then you have to draw the right side, the same as the left-hand side. When the left side is the same as the right-hand side, you're not going to get two products. You're going to get one product because the left product will be the same as the right product. So they just give you one product. When you get one product, that means the two things are the same. That means your alkene must be symmetrical. Okay. So not only that, I can think about this in terms of, let's say, if I have H, if I change this to H, yeah, and then I will have H, then this one can have cis and trans. Now they will combine this with geometric isomerism because I have a carbon-carbon double bond. I have two groups that are different on the same carbon of the carbon-carbon double bond. Then you say they are not symmetrical. They are not symmetrical, Jua, because this is not the mirror image of that, and they cannot rotate freely. Okay, but when you break this is now RCH double bond. And when you have RCH double bond, you are not going to get ketone. What you're going to get is you're going to get carboxylic acid. How about on the other side? You're not going to get aldehyde or ketone. You're going to get carboxylic acid. And guess what? It's still the same product. Then you say, but these are different positions. But hey, hang on. You can draw this as this because you can flip the molecule around and they give you the same thing. So cis and trans, they will give you the same product as well after you oxidize the alkene. Okay, so we're going to go back to this question now, and hopefully it makes sense to you. Now, all three compounds readily decolorize bromine. That means it confirms there is carbon-carbon double bond. So P and Q do not exhibit stereoisomerism. Remember, stereoisomerism could be optical, could be cis and trans, but in the context of this alkene, most likely we are thinking about cis and trans. Okay, it could be optical as well, but we are not looking at the chiral center. Now, R exists as a pair of cis and trans, and as you could see, R only gives you one product. So if you have the cis and trans and you get one product, so that means it's a symmetrical alkene. So there was a very reason why I show you those examples just now. Let me work with R first. So what you get is you get a carboxylic acid. Okay, you get a carboxylic acid, you get ethanoic acid. Now they ask us, what is the original alkene that gives us the carboxylic acid? Well, I'm just going to draw carboxylic acid, ethanoic acid, 2 carbon carboxylic acid, 2 carbon carboxylic acid, stitch them up together. What you're going to get? You don't know the alkene, but guess what? This carbon here is got a CH3H because you get a carboxylic acid from the RCH double bond. You get a carboxylic acid from the RCH double bond, and you get only one product because they are the same product from the symmetrical alkene. So what I get is CH3H double bond like that. Then you check back. When I break this, RCH double bond, 2 carbon, carboxylic acid. RCH double bond, 2 carbon carboxylic acid. So these are R. So that means this must be compound R, sorry, because that is the alkenes that you cleave, that you oxidize extremely under hot concentrated acidic bicarbonate, and you get these products which are the same, ethanoic acid. And guess what? R exists as a pair of cis and trans because what I have drawn here, they are on the same side. That is what you call cis. And then I can draw the other one, which is trans. They want structural formula. There is no way you can write structural formula of cis and trans because structural formula just have different structural formula. But stereoisomers have the same molecular and have the same structural formula. So it doesn't matter whether you write cis or trans, they're going to have the same structural formula. Of course, then R I can just write CH3CH double bond CH3. Is everyone okay so far? Can you follow that?
Yes.
Well, Rahman was the one who asked the question, but can the other follow that at all? I mean, I've been talking for about 5 minutes, 5 to 10 minutes. Everyone else okay? Hello.
Yes.
Okay, all right. Now P and Q do not exhibit stereoisomerism. So we have a CO2 here. what does CO2 suggest about the identity of the alkene originally? What does it tell you, Isa, when you have CO2? What does it tell you about the alkene, Isa? Hello, hello, Isa. Okay, Rahiman, what do you remember about CO2? About the alkene that will give you the CO2?
Primary.
No, there is no such thing as primary alkene. It's a CH2 double bond. That's what you call it, CH2 double bond. Okay. Anyway, so the P will give you CO2 and they will give you C3H6O. Now, S reacts with 2,4-DNPH and you get orange crystalline product. It does not react with phthalings. Phthaling is the test for aldehyde. So if you don't have aldehyde, because it does not react with that, but it has carbonyl. So what we can say is S is ketone. S is a 3-carbon ketone. What is the name for 3-carbon ketone? Let's ask Akila, what's the name for 3-carbon ketone? Akila, hello.
Propanol.
Propanons, and you should be able to sketch what is a 3-carbon ketone as well. It will look like that, And then you have a CO2. And this one comes from CH2 double bond. And this one, it will come from RCR double bond. So it's a C, CH3, CH3 like that. Hopefully, you'll be able to work backwards. And you can see that when this breaks, this will give you the CO2. And this thing is RCR double bond. It will give you the 3-carbon ketone, which is the propanon. So S is propanon, CH3C double bond O, CH3. You can also write it as CH3C bracket O, CH3. Both of them are correct. So P is going to be CH2 double bond, C, and then CH3, CH3. Let's try and name this alkene. We have to try and do naming. Okay, we have to try and do naming. So all of you try the naming. I'm going to ask one of you to give me the name in 10 seconds, because you know it's supposed to be able to get names in 10 seconds. Okay, Shakira Nabila, what have you gotten for me? What is the name of this alkene?
Methylpropene.
Methylpropene is correct. So I could do 1, 2, 3 like that. So my double bond will have 1. So technically it's 2-methylpropene. It's not just methylpropene, it's 2-methylpropene, but that's perfectly fine. So Q, on the other hand, Q will give me CO2 and 3-carbon carboxylic acid. So the CO2 tells me that I have a CH2 double bond, and then I have a carboxylic acid, and then I have CH2, CH3 like that. So I just joined this up. So it must have RCH, and then the CH2, CH3 maintains the original position, but I have an RCH double bond that give me the carboxylic acid. So this one must be CH2 double bond, and then CH bracket CH2, actually I don't need a bracket, CH, CH2, CH3 there. And this one, the name would be 1, 2, 3, 4. That will give you alkene at position 3. That is really, really bad naming. So we don't go for that. We have to go for the other position. This is 1, 2, 3, and 4. So this is but1-in, which is the correct name there. Okay, we're just coming to an end now. Explain what is meant by stereoisomerism. For 2 marks, you must have same molecular formula and same structural formula. But what is different? Different arrangement of the atoms or the groups in 3 dimensions or in space. They want you to draw the display formula of the geometrical isomers of R. So just now I've shown you this was R. So it's this thing here. They want you to draw display. So that means you have to show every single covalent bond. Since they want you to draw display, so you show every single covalent bond. This is on the same side, so it's cis, and this is a but2-in. It's a position isomer of this but1-in earlier. In terms of reduction of the ketone, so S was the 3-carbon ketone that Akila mentioned just now. So this one, plus your reducing agent, and then it will give you the alcohol. And of course, I need to write equation for that, C3H6O plus my reducing agent, which I write as this square bracket hydrogen, and I count this as hydrogen atoms, by the way. So there's C3H, 3 hydrogen is 6, 7, and 8. And I could see that I have more hydrogen here. So I need 2 hydrogen to balance my equation. Now this reducing agent, very popular, lithium aluminium hydride, and your product, you gotta name it just now, you gotta name it, and that will be propent to all that. All right, I've only managed to do 2 questions because I've gone through quite a lot of concepts along the way, but make sure you do complete this question as well. It'll be trans to grow the trans isomer. I think that's all the time we have today, but before we do leave, so maybe we can all just take a quick attendance before you go. Let's just turn on our camera and yeah, take a quick attendance before you go. Hello everyone, hopefully you're still okay. I mean, a lot of key concepts covered today, but I mean, it's all AS, it's only 2 or 3 topics in AS, okay? Still waiting for Akila and I don't know who's the other one, Yasmin, is it? Hello Akila, are you there? All right, ready? 1, 2, 3, smile, you're on camera. We're gonna take another one. 1, 2, 3. Oh, hang on. Okay, hang on. 1, 2, 3. All right, all good, guys. I will upload the PDF. There are a lot of other questions to do still. I can continue more on organic next week, but it's best if you have done the questions yourself and you can ask me to go through whatever other things you want me to go through. But obviously you see how long it took to just go through 2 questions and the concepts. There's a lot more to be done on your side, essentially. Okay, and you can of course use as much of my topical playlists as much as you want or as little as you want. It's really up to you. They are all for free, and feel free to just share them with friends and other chat group, etc., etc. Okay, all right, see you guys then. The recorded session will be uploaded either later on today or tomorrow. Thank you, everyone.